Now let us shift to image segmentation. If speech recognition is about mapping sound to language, image segmentation is about mapping pixels to structured visual understanding. Given an image, the goal is to assign a label to each pixel. This could be semantic segmentation, where each pixel is labeled with a class such as road, car, or pedestrian. It could be instance segmentation, where each object instance is distinguished separately. It could also be panoptic segmentation, combining both. The core challenge in image segmentation is spatial reasoning. Unlike image classification, which outputs a single label per image, segmentation requires dense prediction. Every pixel matters. The model must understand both local texture and global context. A pixel belonging to a car may look similar to a pixel belonging to a bus. The distinction depends on the broader shape and surroundings. Convolutional neural networks are central to image segmentation. Convolutions exploit spatial locality and weight sharing. Early layers detect edges and simple patterns. Deeper layers detect more abstract structures. However, standard convolutional networks for classification reduce spatial resolution through pooling. For segmentation, we must recover fine-grained spatial details. One influential architecture is the fully convolutional network. In this design, fully connected layers are replaced with convolutions, allowing the network to produce spatial output maps. The model downsamples the input to extract high-level features and then upsamples to restore original resolution. Upsampling can be performed using transposed convolutions or interpolation. Another key architecture is the U-net. It consists of an encoder path that captures context and a decoder path that enables precise localization. Crucially, U-net includes skip connections between corresponding encoder and decoder layers. These connections allow high-resolution features from early layers to be combined with high-level semantic information from deeper layers. This improves boundary accuracy. More advanced segmentation models incorporate attention mechanisms, multi-scale feature fusion, and pyramid pooling. The idea is to capture context at different spatial scales. A small receptive field captures fine details. A large receptive field captures global structure. Combining both is essential for accurate segmentation. Instance segmentation introduces additional complexity. It is not enough to label pixels as car. We must distinguish car 1 from car 2. Architectures such as mask-RCNN extend object detection frameworks by adding a parallel branch for predicting segmentation masks. The model first proposes candidate object regions, classifies them, and then predicts a pixel-level mask for each region. Training segmentation models requires annotated data where each pixel is labeled. Creating such datasets is labor-intensive. For example, datasets like cityscapes or COCO involve extensive manual annotation. This highlights a recurring theme in AI: data quality and quantity are critical. The loss functions used in segmentation are typically pixel-wise cross-entropy losses. However, because of class imbalance, alternative losses such as dice loss or focal loss may be used. In medical imaging, where foreground objects may occupy only a small fraction of pixels, specialized loss functions are essential. Let us now compare speech recognition and image segmentation at a conceptual level. Both involve structured outputs. Both require modeling dependencies among output elements. In speech recognition, output tokens depend on previous tokens and global context. In segmentation, pixel labels depend on neighboring pixels and object-level coherence. Both domains benefit from hierarchical representation learning. In speech, lower layers capture local spectral patterns, higher layers capture phonetic and lexical information. In vision, lower layers capture edges, higher layers capture object parts and semantics. This hierarchy emerges naturally in deep networks trained end-to-end. Both domains also face generalization challenges. A speech recognizer trained on one accent may perform poorly on another. A segmentation model trained on urban European scenes may struggle in rural Asian environments. Domain adaptation techniques attempt to bridge these gaps by aligning feature distributions or fine-tuning on target data. Another shared principle is the use of pre-training. Large-scale self-supervised learning has become dominant in both speech and vision. In speech, models are trained to predict masked segments of audio or future frames without labeled transcripts. In vision, models are trained on large image datasets using contrastive or masked image modeling objectives. These pre-trained models learn general representations that can be fine-tuned for segmentation or recognition tasks with less labeled data. We should also discuss computational considerations. Speech recognition systems must often operate in real time, especially in interactive applications such as voice assistants. This imposes latency constraints. Models must balance accuracy with computational efficiency. Techniques such as streaming architectures and model compression are critical. Image segmentation, especially in autonomous driving or medical imaging, also has real-time or near real-time requirements. Processing high-resolution images with deep networks is computationally intensive. Therefore, architectural efficiency, hardware acceleration, and quantization techniques play important roles. Ethical considerations arise in both domains. Speech recognition systems may perform differently across demographic groups, leading to fairness concerns. Image segmentation in surveillance applications raises privacy issues. Robust evaluation across diverse populations and scenarios is essential. From a theoretical perspective, both tasks illustrate the challenge of mapping high-dimensional continuous input spaces to structured discrete outputs. The models must learn invariances and equivariances. In speech, temporal shifts and variations should not change meaning. In images, small translations or lighting changes should not alter object identity. Convolutions and attention mechanisms encode certain inductive biases that help achieve these invariances. Finally, consider the broader AI architecture perspective. Speech recognition and image segmentation are often components in larger systems. A voice-controlled robot uses speech recognition to interpret commands and image segmentation to understand its environment. The outputs of these modules feed into planning and control systems. Therefore, modular design, interface definition, and error propagation analysis are important. If the speech recognizer makes an error, the downstream system may misinterpret intent. If the segmentation model mislabels an obstacle, a navigation system may fail. Understanding uncertainty and propagating confidence estimates through the pipeline is crucial. In summary, speech recognition transforms temporal acoustic signals into linguistic sequences using probabilistic and neural sequence models. Image segmentation transforms spatial pixel arrays into structured scene representations using convolutional and attention-based architectures. Both tasks embody the core principles of AI: representation learning, structured prediction, probabilistic inference, optimization, generalization, and system integration. By studying them deeply, we gain insight into how modern AI systems perceive and interpret complex real-world signals.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.